Chapter 7, problem number 20. This problem is asking to find the acceleration with different coefficients of kinetic friction. And here's a picture of the problem. Basically, the two blocks are compressed. They compress a spring together. They're not attached. And once the blocks are released, they each go sliding at different directions, and the spring just left in the middle. Okay, so for the first part, it wants us to find the acceleration with mu equals 0. So we're given our mu, our mass, our delta x, and our k. And first, what I did was draw a free body diagram for the first block. We have the normal force and gravity, and then the force of the spring acting on the block. So then I did the sum. Well, first the force is the spring equals kx. So I did the forces in the y equals n equals mg. Forces in the x, the force of the spring, which equals ma. And then I solved for a, and I got 1.232 meters per second squared. And I also checked my units at the top. We have newtons over meters times meter over kilogram, which leaves us at the end with meters per second squared, so our math is right. Then we move on to block 2 with mu equals 0. We have our mass, our delta x, and our k. Free body diagram. It looks pretty much the same as the first one. It's just acting in the different direction, but I kept my axis so that the acceleration is positive. Forces in the y, n equals mg. Forces in the x, force of the spring equals ma. Solve for a, and I got 0.616 meters per second squared. So then part B, it's asking us to do the same thing, except mu is now 0.1. So we have our givens and another free body diagram right there. And this time we have the normal force and gravity, and then we have the force of the spring, and then in the opposite direction we have friction. And so the forces in the y, n equals mg. Forces in the x is the force of the spring minus friction equals ma. And I know that friction, since it's moving, equals mu times the normal force. And from some of the forces in the y, I got the normal force equals mg. So we can replace F with mu mg. So kx minus mu mg equals ma. Solve for a. Plugged in my numbers, and I got 0.252 meters per second squared. Then I moved on to block 2, and the only thing that changes here is the mass. I kept my acceleration still positive. The force of the spring acts in the positive direction, and the force of friction acts in the negative direction. So force in the y, n equals mg. Forces in the x, the force of the spring minus friction equals ma. Use the same equation, kx minus mu mg equals ma. And when I plugged in my numbers for kx, I got 0.308, and that's the force of the spring. And for mu mg, that's friction, I got 0.49. And since 0.308 is less than 0.49, there isn't enough force to overcome friction. Therefore, the acceleration is 0. Okay, and so for part C, our mu is going to be changed to 0.462. All of our other constants stay the same. And another free body diagram for the block 1. We have the normal force, gravity, force of the spring, and then friction acting in the negative direction. For the sum of the forces in the y, n equals mg again. Force of the in the x, we have the force of the spring minus friction equals ma. Use the same equation, and when I plug in my numbers, Again, for the force of the spring, I get 0.308, and for friction, I get 1.1319, and the force of the friction is greater than the force of the spring, so again, we have no acceleration. And for the second block, we have all of our givens again. Our free body diagram looks pretty much the same as before. So then we get some of the forces in the y, n equals mg, some of the forces of the x, force of the spring minus friction equals ma. Got our equation there, plug in the numbers, and we get force of the spring 0.308 again, and it's less than the force of friction 2.2638. So again, we have no acceleration. And basically what this problem was showing was that with the two different masses, how friction affects